only thing that's standing between you and lunch, so I will try to be as concise as possible with this presentation. This presentation represents a much larger project that started at the University of Notre Dame last fall. Dmitry Zaytsev and Michael Coppedge are co-PIs on the project that has taken on an ambitious task of trying to predict democratic development and decline. The project is called AIM-3D, which is AI-based modeling for democratic development and decline. I have to say that in social sciences, applying machine learning models have been a daunting task for multiple reasons. Number one, the data that social scientists work with is much more noisy. I'm sure you realize how much the noise can interfere with the signal, especially when we don't even know how much of that latent factor is driven by a signal versus the noise. Number two, transparency and interpretability of models has been also a big issue. And there are certain models out there that can like sharp relative values, line, etc., that can help us interpret what we see, but we don't understand for the most part why we have achieved the results that we have achieved. So the adoption of AI-based modeling has been somewhat limited in social sciences, and in political sciences there are only a few groups worldwide that work with AI-based modeling of any kind. So this project started last fall, and this particular paper represents kind of, it's a continued story of a pipeline that one of the papers was already presented with Michael Coppedge as the first author at their annual meeting of the Political Science Association, which talks about how do we use neural approaches to modeling democratization. Right? So it laid the theoretical foundation. It also talked about the data we're using. The data set is the premier data set in democracy. It's called VDEM. Michael Coppedge is the PI of this project, or co-PI of this project, and it has been in progress for 10 years. So we have 10 years of very, very good data that has been ahead of its time. It has over 200 variables that measure democracy, but those variables are so highly correlated that none of the methods, even some advanced methods such as vector regression, are not able to disambiguate that multiple unit. So we took on the task of trying to do that. So, but the theoretical model of how we model democracy, what is the theory behind it, that's the first paper. The second paper, From Causal Discovery to Dynamic Causal Influence in Nonlinear Time-Series, is forthcoming in Conference of Knowledge Discovery and Data Mining, also known as KDD. That is the paper that lays the foundation for our pipeline. How do we put together different neural network models and time series predictive models to work on this panel data? So it's not just time series, it's also panel data, highly collinear, where we're trying to disambiguate the relationships between variables. We have chosen Bussmann's 2021 NAVAR model, which is neural additive vector regression. From what I understand in computer science, that's an ancient model. It's been around for 5 years, right? And one of the questions we often get is, why did you get some other model? Take 22 is much more accurate. As I said, one of the biggest tasks we're facing is interpretability, explainability. We need to be able to understand what is happening with the data and what the data is telling us at every particular point in time. So NAVAR allows to disintegrate the model into component pieces. So each time series, and the model is broken into time series, and at each time series, every variable is its own neural network. So we can extract those neural networks, we can look at what is happening, and we can build functions of influence of one variable over another, or variables on each other, I should say. So that's what that paper is talking about. And so their ICML paper is actually taking this function value causal influence, it's also forthcoming, and helps explain why some of the relationships we're observing could be negative, even though they expect them to be positive, or some will not be existent, even though we expect them to be there. So there's a lot of explainability that we have extracted from that NAVAR model, and as far as we know, that's the only model that is capable of doing that. So the trajectory aware reliability modeling is forthcoming in the SATR3D, and that one talks about which metrics do we use to evaluate these modeling pipeline, because standard things such as mean square error or MCE, they are not necessarily applicable to social sciences where people have learned to trust data based on p-values. So what are the metrics that tell us which model is better than the other? And so finally, this paper is, once we have the causal relationships between the variables, how do we know which of these relationships are actually necessary for building forecasts? Because even though we're talking it's modeling democratic development and decline, the ultimate goal of science is to build forecasts. So we're trying to develop a model that will build forecasts, and actually the prototype, the working prototype of our pipeline is available on our website. So, going back to the modeling pipeline, most of the models that use neural autoregression or anything similar end up giving neural causal scores. Navarre does that, Tink's model does that. Actually, almost any model that I can think of, I can't think of any model that will give us something other than a causal score. Well, there are problems. Number one, those causal scores are often treated as coefficients. In the case of a simple linear regression, it's a beta coefficient or a slope of the influence of one variable over the other. Well, neural causal scores are also interpreted as analogous to those coefficients, which actually is not very accurate. Depending on the model, in Bosman's Navarre, it's an additive model. It may not necessarily represent their structure of the influence, and the Navarre itself provides a standard deviation of the influence of one variable over time, not even the score itself. Well, actually, most of the political science data has incredible temporal persistence. So the autoregression, the influence of one variable in itself, is typically trumps everything else. So when we have that persistent inertia, how do we account for that, and how do we interpret the causal scores surrounding this persistent inertia? And so that leads to misleading conclusions. Sometimes people end up selecting redundant predictors into the model. Sometimes they select the predictors that should not be there. Sometimes they do not select those that should, based on the causal scores. So the key question, and this is what this paper is about, if we look at this causal matrix that we generate, is the relationship that we're observing required for building a forecast? So understanding causal inference, and we're talking about range of causality here, obviously, is not necessarily their ultimate goal. The ultimate goal is to build a model that will tell us how do these relationships change over time. So we are talking about the forecast necessity, where we define a causal relationship as forecasts necessary if removing the predictor from the model significantly alters the results in a statistically meaningful way. Okay, so basically, we are using the Diebold-Mariano edge ablation procedure, where we use the counterfactual approach. What if we remove this model, with this variable from the model, what will happen? We also look at the observable forecast degradation. So if we remove the model, what happens to the forecast? Does it become worse? Do the relationships change? And like I said, we are using the Granger style causality, not the traditional classical causal effect. Because obviously the models are nonlinear, and we're using them in regularized settings. So we use the origin again, Bosman 2021, Navarre model with modifications. So the pipeline we have on our website will include those modifications. It's adapted to accept unbalanced data, final time series, and many other issues that are plugging the social sciences. So Bosman's original paper was regulating financial data where the errors are minimal. We are dealing with large measurement errors. So there is a little bit of pipeline improvement, but in essence, each target variable becomes its own neural network. And what happens is, it's a shallow neural network. It's a one-time period neural network. We do add an L1 Basser penalty to drive small effects to zero, so that we don't have as dense of a matrix to take forward. For this particular training, we are taking 8 lags of data. We're going back 8 periods, which is already a big improvement in social sciences. I know for computer sciences may not seem to be huge, but in most papers published in political science, people are using 1 or 2 lags because that's all the models can handle. So even using 8 lags is a big improvement, but our model obviously can take a lot of different lags. And we have tested a large variability and of lags, and we didn't really find substantial model improvements with larger lags, but the cost of training obviously is much higher. So we have settled on 8 for now, with an ability to change it to anything we need to change it. And so then basically the causal score represents the standard deviation of the influence of one variable over the other over this 8 lag periods. It does not say anything about forecasting system. So then we use the Diebold-Mariano edge ablation procedure, where we take the entire pool panel. For this particular data set, we take about 20 years worth of data starting with 1990. In some of our papers, we use the same VDEM data set going back to 1900s. And then, so basically, it's a traditional DM procedure where we zero out Fij at evaluation time. We see what happens to the loss differential. And then we use typically one-sided DM test because the matrix is not symmetric. And so this represents the entire data set goes back to 1789. Like I said, it was published first in 2016, was way ahead of its time, because the tools available at that time, and mostly using political science, such as linear regression or even more advanced models, could not capture the nuanced differences between the data. So we have the period for post-Cold War. We have 139. This is a fully balanced panel for this particular paper. 35 years per country, and we use the first 30 years to train, and then the last 5 years of each country to validate the data. So again, this domain shows strong persistence, strong autocorrelation. We have correlated predictors, so variables cause each other, and they are correlated in 0.8, 0.9 range. And then, of course, there is a lot. In political science, a lot of these models drive policy on a local level, so obviously there's a lot of implications for this particular. So this is the global causal structure from Navarre scores. The diagonal is zeroed out, and the matrix just shows their, we zeroed it out because there is strong dominance of this. So if we didn't zero out the diagonal, that's all you will be able to see, because you will see that the range of those standard deviations is actually very, very small. You cannot see it on, I don't do it very well, but it goes from about 0 to 0.07. So it's actually very small scores, right? I mean, we are working with data that's standardized between 0 and 1. So 0.07 standard deviation is not that large. But overall, you can see that it's a sparse matrix. It's a sparse matrix. And when we apply the DM ablation procedure, we actually determine that the matrix becomes even sparser. So despite the fact that these 16 components of democracy are very, very highly correlated. So when you look at most of them, they start correlations 0.6, move up to 0.9 range. There are some relationships that are not as strong. For example, suffrage as a variable is not a very well-behaved variable, because once women acquire rights to vote, then they typically keep those rights to vote, so it stays very stable over time. But you can see the matrix is not symmetric. Just because one variable is causally necessary for another doesn't mean that it's a reciprocal relationship. And so when we took this forecast necessity testing, this is just a comparison of two sources. One is equal protection and one is equal access. You will notice that the source 2 has actually a higher standard deviation of higher Navarre causal influence score, but they have almost identical mean loss for the full, and then there is quite a bit of a mean difference for the masked, and the DM statistics is statistically significant for one, but not for the other. So a higher causal score does not necessarily mean forecast necessity. And that is the biggest finding of this work. Now, local explanations also confirm the DM results. We just use the SHAP to see what happens, and then you can tell that the source 1, equal protection, is consistent, recurring influence. Equal access, not that much. I know you cannot really see that easily on this image. If we remove suffrage, which is, again, a very persistent variable, then you can see these differences much, much better. And so the basic, lessons from this particular paper is that redundancy between the variables inflates without applying this forecasting system. So we can keep some variables that have high causal scores, but they're not necessary for forecasts, which creates erroneous forecasts or very noisy forecasts. Just because something has large causal score does not mean it's stable. That causal score over time could be generated by a single spike, then gets zeroed out, so that variable is not necessary. And then we are also shifting from parameters to behaviors. So we look at these causal claims and the observable changes that we have to the predictive accuracy. So this creates a much more robust, transparent, and defensible pipeline than just coefficients. And obviously there are limitations, quite a few of them. It's model specific, even though we have found that, as I mentioned, we use this data set in a variety of different combinations. The relationships between those democracy variables remain very stable, despite different years, number of countries, etc. So the process is the data generating process underlying the data is very stable. So we're getting very similar results. It's still single domain. We don't know how this would apply to psychology or other social science data. The Diebold-Mariano test is conservative, so we are probably committing a type 2 error somewhere in the process, which we're going to live with. We did have correction for multiple testing, because obviously when we have n times n minus 1 edges, that does inflate the family-wise error rate. So we have applied Bonferroni, but we can use some other corrections to it. And then obviously the scalability is still sure. So the core finding, the causal score magnitude and forecast necessity can diverge. Just because something is shown to be causal in a neural network model does not mean that it needs to be used in further modeling. Ablation allows us to estimate that particular necessity. And the broader argument is if we are focusing on prediction, then we do need something more reliable than just coefficients in nonlinear.